Hello, everyone. As we're starting to come back, Dana has a survey that she's going to put the link up into the chat, I believe, if I'm correct about that. Dana, speak up if I'm wrong about that. We'd ask you, I think it's 4 or 5 questions, if you could just take a quick moment and go follow the link. And if you could respond to those couple questions in there, it'll take you just a minute to do it. We'd appreciate it. Help us as we look at TOPCORP and the future and how we do our planning and topics and such. So Dana has it in chat now, and we'll get started with David. We're going to start this afternoon with a friend and colleague from Penn State, and that's David Yoxtheimer. Dave is an assistant research professor, extension associate, and a hydrogeologist. I wish you had picked an easier major like history, David. Hydrogeologist with Penn State, with MCOR, which is our Marcellus Center for Outreach and Research, and serves as a liaison to advise stakeholders on key environmental issues. He earned his BS in Earth Science from Penn State, where he completed his PhD in geosciences. Before joining Penn State and MCOR, he spent 18 years as a consulting hydrogeologist with expertise in water supply development, karst hydrogeology, geophysical surveying, environmental permitting, shale energy geology, and integrated water resource management. Dave is also a hydrogeology instructor at Penn State and was recently appointed by our Pennsylvania Governor Wolf to be a voting member of the Pennsylvania Department of Environmental Protection's Oil and Gas Technical Advisory Board. And congratulations on that, Dave. I know it's a task. You take all the hard ones under your arms and grip onto them and run with them. So with that, we invited Dave to come this afternoon and talk about flowback and produced fluids management. With that, and just as a reminder to everyone, if you, when Dave's finished, we'll have, give or take, about 10 minutes afterwards for questions directly to Dave with regard to the presentation and the topic. So make notes, mental notes, pencil notes, and be ready for Dave. Dave, I'm going to give it all to you. Thank you for joining us. Thanks for taking the time to be with us. It's all yours, Dave.
Excellent. Well, thanks for the nice intro there, John. If we made it any longer, probably would have taken up my entire 35-minute presentation time. Well, hi, everybody out there. I hope I've got everybody from the East Coast to the West Coast and up to the North in Canada. So it's nice to have everybody out there. I'm going to give kind of a, broad overview on flowback and produced fluids management. We heard some, discussion of that in the breakout sessions a little bit on the feedback there. And it's becoming a stickier and stickier situation out there, managing the fluids as the price of the commodities are depressed, and it's a significant cost to manage these fluids. So we'll go through some of the different strategies that are being used out there, and then we can talk about some of the innovations as well, as I know that came up earlier too. Again, big picture here, when we think about shale energy water management, we're talking about everything from you might be using surface water like we do more so here in the Appalachian Basin. And if you get down into some of the more arid regions, you may see more and more groundwater be used. And I know up in Canada, at least in some of the plays, they actually use saline groundwater. So, whatever's available and abundant is typically the source of water that's used. So those waters are transported to the site, the drill site. It's getting ready to be fractured, blended with the chemicals, injected at sufficient pressure to break down the rocks, the shale, or in a conventional formation, maybe the sandstone or other type of formation, down into the shale. We're talking about millions of gallons or tens of millions of liters. A typical frac job in the, for instance, in the Marcellus, you're looking at about 10 million more gallons, or roughly approaching 40 million liters of fluids to fracture these wells. Each play is different on how much water what the chemical blends are to optimize the overall process, but that gives you a sense of the scale. And if you really want to kind of break it down a little bit more, we're seeing longer and longer well laterals being drilled, so you're going to need more and more water. But you might want to think about, for each, roughly 1,000 feet or so, or maybe 300 meters of a well, you're going to use on the order of, 1 million to 2 million gallons for every 1,000 feet, or roughly 4 to 8 million liters for every roughly 300 meters. So, significant amount of water used during the fracturing process. And then a portion of that water is going to come back out of the well, especially during the flowback period. You're going to have an initial surge of return fluids. Typically, we call that the flowback. And then once the wells are put online and producing hydrocarbons, then you're going to get the produced fluids. So it's really the same fluid stream, sort of just a semantics as far as the terminology, whether you're waiting to bring the well online, it's flowback, and after the well is brought online and commercially producing hydrocarbons, it's produced fluids. And so what we're going to do is focus on that produced fluid handling side of things here, and look at wastewater disposal and reuse. This is just kind of a different graphic showing the different phases. So again, the water acquisition, chemical blending or mixing, injecting the fluids at high enough pressure to break down the rocks. Here in the Marcellus, you're looking at somewhere between roughly 8 to 12,000 psi. Kind of depends on the depth of the formation and the frac pressure gradient necessary to fracture the rocks. And then you're going to, again, as I mentioned, get a return of fluids initially. That's the flowback water, and you're going to have the right storage capacity, whether that's tanks, more permanent tanks, modular tanks, and then you're going to have to figure out what to do with those fluids on the back end. Are you disposing of them? Are you recycling the fluids? If you're recycling, what treatment technologies may be appropriate? If you're disposing, what disposal methods appropriate? So we'll get into some of the details on that. So again, just kind of reiterate, there is a distinction between flowback and produced fluids. When you're introducing fracturing fluids into the formation, it's mostly water with proppant, typically sand, along with an addition of a variety of chemicals. Depends on whether you're in a dry gas play. It's going to tend to be a simpler chemistry versus getting into the oil window in some of these shales, where you're going to tend to have cross-links or cross-linked fracture fluids, or maybe more gels involved, which get more chemically complex. And again, so when that initial surge of water comes back out, or fluids, I should say, really come back out, you're going to have a higher proportion of the fracturing fluids that were injected down in there, and perhaps some of the native waters. And then as time goes on and more of those fracturing fluids sort of flush back out, you're going to have a greater and greater proportion of the native fluids down in the shale or producing formation. And so that's going to tend to change the chemistry of the fluids that are coming back out of the hole. And it's also going to, may dictate what kinds of reuse capabilities you have and what kind of treatment options you may need. So as I'm kind of insinuating here, there's going to be different approaches for different basins, and this is just a compare and contrast between the Marcellus up here in Pennsylvania and the Appalachian Basin versus what has gone down on in the Barnett Shale in Texas. And so on the left-hand side of these graphics, we're looking at what kind of water sources are being used. And as I mentioned, here in the Appalachian Basin, you're seeing mostly surface water used. Fluids are recycled here, which I'll talk about. So some of the flowback and produced fluids are mixed back in with fresh water and sent back downhole for hydraulic fracturing. A little bit of groundwater, not that much in this part of the world. But if you contrast that with the Barnett Shale, it's about equal parts groundwater and surface water with a little bit of reuse water blended in there. In the Marcellus, recycling occurs at a much higher rate than really any other shale basin. We look at recycling rates of flowback and produced waters of about somewhere between 80 to 90% typically, whereas many other basins you're looking at typically less than 50%, maybe 10 to 25%, something like that. So again, it varies. Some of that's based on the regulatory framework you're working in within that state, what's allowed, what's not, as well as the compatibility of the fluids. If you're going to send reuse fluids back down, you have to make sure they're going to be compatible with the formation, plus whatever disposal capacity. Again, once we look on the back end of the fluids on how they're being managed, as I mentioned in the Marcellus, you're looking at about 90% recycling of the fluids, which means you need less fresh water and less treatment and disposal. Whereas in Texas, in the Barnett at least, you're seeing about 95% of the fluids basically disposed of down a class 2 injection well with just about 5%. And these numbers are 4 or 5 years old, so they may be a little different right now, but it kind of gives you the general sense of there's really this sort of major shift in how we're managing these wastewater streams with shale energy development around the U.S. and hopefully you'll be able to share a little bit of what some of your experiences are here a little bit later. So then if we look at hydrocarbon and brine production per well, this is from Kondash et al. From a couple years ago. The units here are a little awkward. They're talking about millions of cubic meters per well on gas production and cubic meters per well in oil production. It still gives you the sense that, for instance, in the Haynesville, the wells tend to be more highly productive than the other gas plays, shale gas plays. You got the Marcellus coming in sort of a distant second, and then the Permian and Eagle Ford basins way down there. But then that kind of obviously flips back around when you look at oil production. The Eagle Ford, Permian, Bakken tend to be your larger oil producing shale plays here in the U.S. But then if you compare and contrast with the flowback, how much basically produced fluid you're getting back out of these wells, with the Permian, you're getting a significant return of fluid. So that means either, you're going to have a lot more fluids to manage, whether that's through disposal wells or some sort of recycling or other management method. And basically very similar on the oil side. So again, different shales are going to give you different volumes of return fluids, different percent return fluids compared to what was injected down there. And that next slide kind of gets into that. But another thing to consider is, well, how much energy in essence are you getting out of a well for every unit of water you're using? So that's another kind of interesting way or metric of looking at water use intensity. Is it more water efficient? Are you getting more basically energy out per well? And so again, if you look at the Permian Basin, you're using a lot of water for every, in this case, gigajoule of energy you generate on the gas side of things, and here on the oil side of things, basically a similar trend. So basically, what we're saying is your energy return is going to be greater for some shale plays versus the other. So again, not as much energy for the amount of water you're putting down in the Permian. The Eagle Ford kind of coming in second to last, I guess you could say in this case. But then another way to look at it is, well, how much flow back are you getting back versus how much water you put in? And some, for instance, the Permian, you're getting nearly 6 times, well, at least in 2014, as much as 6 times more flow back than water you put in the first place. So you're getting a significant return, which tells you that, there's a lot of native water down there that is going to return back out along with the fracturing fluids. For instance, the Marcellus is very low down here. We get like maybe 10% of the fluids injected down come back as flow back. And then over the course of time, you may get, maybe 50% of the water until the wells ultimately, shut in and decommission. So again, depends on whether you have a very dry shale, maybe it has higher absorptive capacity, or maybe you have water wet shales. There's already some water down there, and they tend to be, the shale might be a little more, if there's enough oil down, it might actually be hydrophobic. So it's going to push the water back out. So again, each shale is going to have different characteristics. And with, looking at the, oil production, gas production versus water use and wastewater production, you can start to play around with these numbers, which can be, really useful from a regulatory standpoint. If you're going to project out into the future, production trends, you might then be able to start to look at, well, how much treatment or disposal capacity might we need in the future, and start to, plan out accordingly. This is an example of water and oil recovery from the Bakken shale. And so what we're looking at here is hours on the x-axis, cumulative flow back on the y-axis. And so if you look at, and this is, a relatively short flow back period, just under 45 hours. And if you look at the numbers, there's a 24-hour recovery of flow back. You got 12% back of what you injected in other words, in 24 hours, and overall about 17% at the end of the day here. So that would be the blue line is what you're looking at there. So a couple things to note if you're not familiar with looking at things like, the oil cut. After you fracture a well, again, you're going to tend to get more of the fluid you injected down in there in the first place back. But as time goes on, you're going to get some more and more oil and or gas, until the point where it's actually commercially productive, and then you'll turn it in line. Basically having 0% oil in the measured cut to somewhere between roughly 30 to over 50%, peaked up to nearly over 80%, and then kind of came back down to right around 65% within less than 48 hours of time. And so again, you can gauge the total flow back volume that you got back. You can look at how much oil you recovered, and then you can look at, well, how much flow back, or I'm sorry, what volume of fracturing fluids are down there yet to be recovered. So again, you can start to understand something about both the production curve on both the flow back side of things, as well as the oil and or gas side of things.
Hey, Dave.
But what we also know is that, yeah.
Excuse me, Dave. Hey, the audio and video is getting a bit choppy. I don't know if maybe shutting off your video might help the bandwidth there or not.
All right.
Thank you. Sorry to interrupt you there.
Yeah, that's all right. I will turn mine off, and hopefully that doesn't mess with anything.
As much as we like to see you. I know. I get it. I
appreciate that. Bear with me here a sec. Okay. All right. So again, as time goes on, you're going to have a change in your water chemistry as well. So again, you're going to get more and more of the native fluids coming back out of the producing formation. These formations are going to tend to have, brines in them. And so you're going to tend to see, the salinity of the return fluids, flowback produced fluids, increase over time and with the volume of flowback that you're receiving. So that's simply what we're showing here in this graph. But then you're going to start to see, different anions and cations that make up that, some of that salinity or the total dissolved solids increase. So you're going to see things like your chlorides increase, your sodium will increase, along with some of your other metals, whether that be, calcium, barium, strontium, you name it. So, the sodium and chloride are going to tend to dominate the total dissolved solids concentration that you're seeing, but some of those other metals may too. As you're probably aware, the barium and strontium are sort of notorious oil and gas field scalants. And so you want to be careful with, what those levels are and how that may affect your equipment. But then this is also something to start to consider when you're starting to look at how best to treat these fluids, if you're going to recycle them or if you need to do some pre-treatment prior to disposal. And so what we'll do is look at, some of the major options out there as far as handling flowback and produced fluids. Again, in the Marcellus, we're kind of unique in that there's a high reuse percent with flowback and produced fluids approaching 90%. I realize that's, tends to be, maybe less than 10% or maybe upwards of 50% in many other basins. But if you are going to recycle the return fluids, you may be able to just basically blend these return fluids in with fresh water and just send it back down the next hole that's getting fractured. The risk there is there might be some plugging potential, whether that's with any dissolved constituents or even like the barium and the strontium, or perhaps with the mechanical or physical plugging with any suspended solids or sediment in those fluids. You could have an on-site treatment and reuse scenario. There's a lot of mobile equipment that's been deployed throughout the Appalachian Basin to actually treat the fluids on site and then recycle them. There might be off-site treatment facilities, but what you're basically doing is, sort of pre-treating the fluids to recycle to minimize that plugging potential and sort of condition the water so it's just right for fracturing. Or ultimately, you'll take fluids off-site and take it to a treatment and or disposal facility, which tend to have higher costs, but each region's different. Basically, keeping the fluids within the field on site, you're going to minimize the transportation costs, which are tend to be rather significant portion of the management process. So anything you can do to minimize the transportation, you're going to minimize those costs. But different treatment strategies are also going to have different costs because of the necessary energy input. So when you think about the various treatment technologies out there and what may work, if you're going to recycle the fluids, you want to minimize your waste volume and minimize your waste volume and disposal needs. If you're gonna, but you also want to have a high removal of the contaminants. Whatever your treatment scheme is going to be, you don't want it to be a very high maintenance operation that's going to run up your labor costs. You want it to be flexible. Again, you're going to have potential significant variability on just total dissolved solids, much less calcium, sodium, chloride, etc. So whatever, if you do have a treatment scheme, you want it to be able to handle both a change in quality, but also perhaps quantity, and be able to be efficient throughout the process. And then if it's going to be on site, you're going to have modular technology. You want to have a relatively small footprint and, overall just a minimal environmental disturbance. So there are a variety of treatment technologies. Some might be more geared towards recycling. Others might be geared towards disposal. What we're seeing has been a sort of an evolution of treatment technologies and application in the Appalachian Basin, where maybe 10 years ago, companies were very concerned about sending reused fluids back down hole and the potential for scaling and plugging up the fractures and therefore reducing long-term production. I think the industry's more or less gotten comfortable with the fact that that risk is pretty low. So we see not so much scalant removal, things like calcium, magnesium, barium, strontium, but more sediment removal. So that's where filter socks come into play. They're not going to take out the dissolved constituents, the ions, but they'll take out the sediment and any suspended solids. Chemical precipitation is a method where you're basically trying to drop out the potential scalants, again, the barium, the strontium, the calcium, but you're more or less probably leaving the salts in. Electrocoagulation is a method, basically achieves similar. It removes the scalants, but it's going to leave the salts in. There are other methods like oxidation that in some cases, if you have low enough TDS, you're not so much concerned about removing those constituents, but maybe changing their valence state in essence. We can also think about methods, more filtration type methods, micro or nano filtration. You don't see that used a whole lot, but it may have some application out there. Reverse osmosis may work if you're trying to desalinate the fluids, but you need to have a TDS level or total dissolved solids level less than roughly 40,000 milligrams per liter. So if you're getting into these more advanced treatment technologies where you're starting to remove the salts with things like reverse osmosis or evaporative methods, your costs are going to start to increase because your energy input is also increasing. We see crystallization used in a couple of facilities here in the Appalachian Basin, where you're actually crystallizing the salts out and creating a clear, in essence, distilled water, which you could actually achieve with the evaporative methods potentially if the TDS is low enough. You know, the evaporative methods will work, you know, up to about 150,000 milligrams per liter of total dissolved solids, something on that order. Whereas crystallization, you may be able to handle, you know, levels of salinity in excess of 300,000 milligrams per liter. But with crystallization, you're going to create a significant amount of salt because that's what you're crystallizing out. Some facilities have actually found a market to sell that salt, which helps with the overall bottom line. But depending on the nature of your treatment, if it's more simple like filter socks, you're on the $2 per barrel side of the cost spectrum. Whereas if you're getting up into the evaporation or crystallization methods, you're starting to get up to near, you know, $10 or maybe more per barrel. And so again, some of these methods really, I would say, you know, the first 4 or 5 are really useful for recycling. If you're trying to, you know, get into like a surface disposal method through an NPDES permit, you might need, you know, an evaporative method or even crystallization. Again, recycling rates vary from basin to basin, so it kind of depends on the regulatory framework, whether you're allowed a surface discharge. I realize that's not allowed in every state, so you might be looking at injection wells, etc. So when we think about, you know, produced fluids for recycling, this is taken from a study that was done probably about 6 or 7 years ago as part of a DOE project, just looking at, and this is actually kind of specific to the Marcellus, but it was kind of a survey from the industry to say, hey, if we're going to recycle, what are our treatment requirements? You know, what kind of water are we willing to send back down hole? And just, I won't go through all of these. You can read them for yourselves, but really the TDS is kind of the magic number. with having less than 50,000 parts per million or milligrams per liter of total dissolved solids. In particular, the chlorides there, because they may interact negatively with the friction reducers. Hardness is something to consider. Barium, strontium, iron, manganese, which could be scalants. You want to have them down less than 10 parts per million. Calcium less than 8,000 parts per million. Total suspended solids less than 30 parts per million to avoid that sort of that physical plugging potential. So again, it's not a hard and fast, but it kind of gives you a gauge on what kinds of levels you're looking at. Again, for the higher limitations, as I already mentioned with reverse osmosis and evaporative methods, these are approximate, but again, give you a typical gauge. And really, with crystallizers, you can get up to about 300,000 TDS, milligrams per liter of TDS before you kind of swamp the system. Again, in Pennsylvania, because we do a lot of recycling, you see about 2/3 of the fluids recycled out in the field. One of the innovative methods out there is actually taking waste heat off of compressor stations to use that as your energy source for distilling the water from the salts. So that's just one of those, it's a free, in essence, free heat source if you can figure out how to tap into it. But there's just about any method you could imagine needing treatment for, there's somebody offering that service out there. And just kind of break things down here quickly in the next couple minutes. Using Pennsylvania as an example, last year, the industry produced about 9 barrels of produced fluids for every million cubic feet of gas produced, and we produced about 6.8 trillion cubic feet of gas in Pennsylvania last year. The recycling rate was about 85%, so 52 out of roughly 61 million barrels of fluids were recycled. As I mentioned, much of that recycling is occurring out in the field using filter socks or mobile treatment technologies. And then about just around 8% of the fluids, or just nearly 5 million barrels of fluids, were sent to disposal wells. Pennsylvania, we don't have a lot of disposal wells. We have 11 operating disposal wells. So the bulk of those fluids that are being disposed of are being sent to disposal wells in Ohio, where they have over 230, I believe, to date. So speaking of disposal wells, again, I know, say down in Texas, you've got, on the order of 8,000 Class 2D disposal wells, and then on the order of 50,000 or so wells for secondary recovery of oil in more mature conventional fields. So you got to look at the geology. Obviously, that's going to vary from basin to basin. Figure out where you have enough permeability at depth with a confining layer, and lack of any nearby faulting would be the sort of in general the geologic conditions. We're seeing more and more seismic monitoring required associated with disposal wells. And then, of course, you have to look at making sure that they are maintained properly and have sufficient well integrity. So generally, the minimum amount of integrity testing is every 5 years. In Pennsylvania, these tend to be very controversial and take years to permit, and much of that's because of the public and legal opposition. I won't go into great detail. I don't want to cut into the question time here too much, but you can get some sort of back of the envelope numbers if you know some of the things like the porosity of a potential injection zone, how thick that zone is, and the basically how much of a area you're going to be injecting into. You can start to figure out, well, how much porosity do I have available to me? And so just kind of running through this sort of simple math, a typical injection well in a sandstone here known as the Oriskany in Pennsylvania may be able to accept about 620,000 barrels of fluids just with the existing porosity. Now that wouldn't include, pressuring it up as you can with an injection well, but that just kind of gives you a sense of what an injection well, at a minimum may be able to accept. And this is the folks, I'm sure, with the EPA familiar looking at, how much pressure you're going to build up in an injection well over the course of time. And of course, you need to keep that injection pressure below the rock fracturing pressure so as to not fracture the rock. And over on the right side of this slide are all the parameters you need to have so you can plug it into that equation to figure out what your pressure is going to be down in the formation to figure out whether you have enough capacity to inject these fluids at a given pressure before you would start to fracture the rock. And just in quick summary here, especially nowadays, the fluids generated from shale oil and shale gas development are ever increasing. And so we're going to need more and more, disposal and treatment technologies out there. Obviously they're going to need to be cost effective while environmentally responsible. And, there are, more and more innovations coming out there with greater efficiency and lower costs. But again, I know this is a tough spot for the industry right now because there is always going to be a cost with it. And as commodity prices are low, it tends to be more and more difficult to, justify the cost and, actually may make shale energy development, sort of technically not cost effective because of that. So with that, I would be happy to address any questions you may have. Sorry that was short and sweet, but hopefully I didn't try to pack in too much there. And it was a pleasure to provide the information to you. So any questions? And I guess I'll leave this up in case anybody needs to go back to a different slide.
Thank you, David. And yes, we've got a couple minutes for questions, so fire away. You can open your mics and speak.
Hey, Dave, this is Larry Harlan. So if 8% of the wastewater is put through disposal wells, is the balance of it in Pennsylvania actually reused in new drilling? I guess that's then trucked to new locations. Is that right?
That is correct. Yeah. So, one of the trends we're seeing is a higher percentage of recycled fluids being blended in to the fracturing fluid mixture. Some operators have done, 100% recycled fluid fracs, not because they really want to, but it almost becomes a wastewater management method for them on some level, just because I didn't really get into the trucking costs with disposal wells here, but most disposal wells are hours away. And so it might be $5 to dispose of the fluids, but it's $10 or more to transport the fluids to the actual well. So some operators have actually just, like I said, gone to using a higher percent of fluids in their fracturing fluid mix.
Okay, thanks.
Sure. And I should also note, if anybody has any questions, I'll let you think here a sec, but we do have the ability now to discharge to surface water if the total dissolved solids of the treated wastewater is less than 500 milligrams per liter. And so that, again, really gets into thermal distillation, evaporative type of technology, and maybe followed by crystallization in at least one case. So we do have a couple of facilities here who actually do surface discharge, but it doesn't make up a significant volume. Other questions out there?
Do you feel, or do you think it might be a possibility that some of the hesitation besides cost, do you think that there's a notion that using produced water, reusing it in another frac, do you think they might feel that it might not give them as productive of a fracturing process using recycled or reused produced water?
Yeah, there's been some different, that's a great question. There's been some different schools of thought out there. I've heard everything from, well, the brine's denser, and so we're putting a heavier fluid back down the hole, so it may actually fracture better. Being that the fluids came out of, we'll just say the Marcellus in the first place, if you have the salts and, other ions in there, it's, you're sending it back down in the formation that it came from. So the fluid compatibility may be a little better, so you don't have as much formation damage. I've heard, you can, if you have a TDS that's, maybe approaching 100,000 milligrams per liter, you can offset that by using more friction reducer, which is going to drive your costs up. But again, if that's cheaper than, sending it to a disposal well, then you can, kind of justify that. So there's some different approaches out there. And I don't know that, there's a universal approach, but that probably gives you a sense of the word on the street. And I'm actually, this picture you're looking at here is actually salt piles from the one facility I mentioned that has a crystallization treatment element. So you develop a lot of salt, which in this case, they actually have found a market for using it in basically as salt for saltwater pools, which, seems a little ironic based on how controversial this fluid stream can be. But that is one of the approved commercial uses out there.
Hello.
Probably have time for another question for Dave.
Yeah, I do have one question. I guess I didn't quite understand why Pennsylvania producers send truck their produced water to Ohio for disposal. Is that because of technical reasons or cost reasons or both, I guess?
It's really because we have very limited disposal well capacity here in Pennsylvania. We allowed surface discharge with the conventional industry for many decades. And so that was just a cheap way of dilution as the solution to pollution. But then as the shale industry really took off, the salinity and the volumes went up, and that surface discharge or running it through municipal wastewater treatment facilities just wasn't proving out to work very well. And so that's where the surface discharge was really restricted unless you could treat the fluids down to basically a high quality effluent. And so that gets costly. So it's not that the industry wants to truck it to Ohio. That's kind of a last ditch option because that's going to be fairly expensive. So that did force the industry to do more recycling, which at the end of the day is a more cost effective and environmentally friendly, I guess you could say, approach. And that, again, we're seeing some disposal wells come online, but not enough to keep up with the demand for them. So I'd imagine, we'll at some point see enough disposal wells to kind of capture those fluids somewhere in Pennsylvania before they get trucked all the way to Ohio.
Dave, I'm going to give you a virtual applause there. Thank you so much for taking time to be with us today and present. And I'm optimistic and hopeful that maybe your time will allow you to be here still at the end. We thank you for joining us early and hanging in there and presenting with us. That was extremely informative, and I picked up a page of notes from this also. So Dave, thank you very much. We appreciate it. Thanks.
Thank you, Dave.
Yes.
Sure, thank you.